All right, let's dive into a massive part of your GCSE physics. We're talking all about waves. Okay, so let's kick things off with a pretty big question. Think about it. How does the sun's energy travel 93 million miles across the total emptiness of space to get to us? I mean, there's literally nothing out there, right? So how on earth does that energy make the trip?
Well, the answer is actually really simple, and it's the key to, well, everything we're about to cover. It's all about waves.
So what is a wave, really? You've got to get this definition down. It's so important. A wave is just a way to move energy from point A to point B. But here's the kicker. It does it without moving any stuff, any matter along with it. The energy travels, but the particles themselves just kind of jiggle on the spot.
Okay, so we've got the basic idea down. Now let's get into the two main types of waves you're definitely going to need to know for your exams.
All right, here's the big difference. First up, you've got transverse waves. This is where the vibration goes up and down while the wave itself travels forward. So they're at right angles to each other, perpendicular. Just picture a classic wavy line, you know? Light is a perfect example. Then you have longitudinal waves. These are different. The vibration is a sort of back and forth push-pull motion that's in the same direction the wave is traveling. Think of sound. It works by squashing particles together, we call that a compression, and then stretching them apart, which is a rarefaction.
So what's the bottom line? Well, sound waves need something to travel through. They need a medium, like air or water. That's why in space, which is a vacuum, you can't hear anything. But light waves, they're special. As transverse waves, they don't need a medium at all. They can zip right through the vacuum of space, which of course is how we get sunlight. And here's a huge pro tip. Seriously, remember this for your exam. Waves move energy, not matter. The particles just wiggle. They don't travel along with the wave.
Right. So we've got the two types down. But how do we actually measure them and describe them with numbers? Let's look at the blueprint for how waves behave.
First up, we have wavelength. Its symbol is that little Greek letter lambda, and it's exactly what it sounds like, the length of one complete wave. The easiest way to think about it is the distance from the top of one wave, the crest, to the top of the next one. And since it's a length, we measure it in meters. Simple as that.
Next is amplitude. This is all about the height of the wave. It's the distance from the middle line up to the very top or down to the very bottom. Now here's the really important part. Amplitude is all about energy. The bigger the amplitude, the more energy the wave is packing. Think about it. A tiny ripple in a pond has a small amplitude. A giant tsunami, that has an absolutely massive amplitude and a whole lot more energy.
And last but not least, we've got frequency. This one's about how often the waves come. It's literally the number of complete waves that pass by a certain spot every single second. We measure it in hertz, which we just write as Hz. So a high-frequency wave means lots of waves are zipping past every second, while a low-frequency wave is much more spread out.
And the coolest part, all three of these things, wavelength, amplitude, and frequency, are connected. They come together in one super important formula you've just got to know, the wave equation. It says that the speed of the wave, which we call v, is equal to its frequency, f, times its wavelength, that lambda symbol.
Let's put it into action with a quick example. Say you've got a wave with a frequency of 5 Hz and a wavelength of 2 meters. What's its speed? Okay, step 1, write down the formula. V equals f times lambda. Step 2, plug in the numbers we know. So v equals 5 times 2. Step 3, do the math. The wave speed v is 10 meters per second. See, not so scary at all. All right, now that we have the tools to measure waves, let's talk about the most famous family of waves in all of physics, the electromagnetic or EM spectrum. This is the big one, guys. These waves are everywhere, and they all travel at an incredible universal speed limit. So here's the whole lineup, going from the longest wavelength and lowest frequency all the way up. We start with radio waves. Then we've got microwaves, infrared, and then that little tiny section our eyes can actually see, visible light. After that, things get more energetic with ultraviolet, X-rays, and right at the top, the most powerful and highest frequency of them all, gamma rays. Now, I know that's a lot to remember, but don't worry, there's a classic, slightly silly way to remember the order. Just think of this phrase, raging men in vests use extra gel. Yeah, I know, but it works. Radio, microwaves, infrared, visible, ultraviolet, X-rays, gamma. Trust me, it'll stick in your head. Okay. Now get ready for something that's genuinely mind-blowing. Every single wave on that list, from a long, lazy radio wave to a supercharged gamma ray, they all travel at the exact same speed through a vacuum. And that speed is 300 million meters per second. That's the speed of light. It's like the ultimate speed limit of the universe.
Nothing can go faster. Period.
So you might be thinking, if they all travel at the same speed, what's the difference? Well, here it is, the single most important point. It's all about frequency. The higher the frequency, the more energy the wave has. That's it. That one simple rule is the key to understanding all their uses and all their dangers.
So let's dive into that right now. Let's look at the amazing things these waves can do and the risks that come with them. This is like looking at the universe's own toolkit. You can see right here how each wave is perfect for a different job. Radio waves, their super long wavelength lets them travel huge distances, which is why we use them for TV and radio. Microwaves are just the right frequency to vibrate water molecules and heat them up. Yep, that's how your dinner gets cooked. Then you jump up to X-rays. They've got enough punch to go through your skin, but get stopped by bone, which is perfect for taking pictures of broken arms. And at the very top, gamma rays are so powerful they can be used to zap and kill cancer cells in radiotherapy.
But as you'd expect, all that energy can also be dangerous. Once you get past visible light on the spectrum, you're entering the danger zone. Infrared radiation is what you feel as heat, and too much of it can burn your skin. Ultraviolet, or UV, from the sun, we all know that can cause sunburn and even skin cancer. And then you get to the heavy hitters, X-rays and gamma rays. These guys carry so much energy they can cause real damage to our cells and even our DNA.
So why are they so dangerous? What are they actually doing? Well, the official term is ionizing radiation. It's a fancy name, but the idea is simple. These high-frequency waves, UV, X-rays, and gamma, have enough power to physically knock electrons clean off of atoms. And when that happens inside your body's cells, it causes damage. That's what can lead to mutations and all the health problems we associate with.
So when you think about it, everything from the sunlight warming your face to the Wi-Fi signal connecting your phone, it's all waves. It's the universe's fundamental way of moving energy around. They're like the secret code behind how everything works. So I'll leave you with this thought. Now that you're starting to understand the code, what other secrets of the universe do you think it could unlock?